Assalamualaikum warahmatullahi wabarakatuh. Hello everybody. Please allow me to take this opportunity to present our research on the certification of nanoparticles to several metal ions. As we know that each material has different characteristics, especially if the material is already in the content shape of size, for example in the size of nanometer. So our research focus on knowing the characteristic of silver material when it is in colloid condition and nanometer size. This research focuses on knowing the potential of silver material when it is in a colloid condition and is nanoparticle size. Broadly speaking, this research focuses on the process of how silver material derived from argentonitrate compounds change to colloid form. Therefore, the process carried is the process of building compounds from the solution into even a large structure, namely from the atomic size to the size of the nanoparticle of or colloid, or what we call the bottom-up method. The formation of nanoparticle involves several processes. The first is reduction of Ag plus to Ag0. This reduction involves secondary metabolite compounds in the form of flavonoid groups from plant extract. And this research, the extract used was extract from green tea. The group that are in the secondary metabolite are known to be terpenoid group, flavones, ketone, aldehyde, amides, and carboxylate acid. Then the ethanol, which is formed, then undergoes agglomeration or collide with each other to form a large part. This is the key to making the desired nanocolloid. The presence of a stabilizer that acts as a lock from a nanocolloid has a function so that it does not develop an colloid into one, so that it will not cross the threshold of the size of 100 nanometer. The stabilizer used is PVA or polyvinyl alcohol. This PVA plays a role in stamping each groove of Ag0 and keeping the particle size from exceeding 100 nanometer. Synthesis of silver nanoparticle was carried by mixing green tea leaf extract and argentonitrate 1 millimole with a ratio 1:20. The mixture was then sonicated for 15 minutes and then stirred on a hot plate and gradually added PVA solution. The detection of metal ion was carried against CD, Cu, Pb, Mn, and Zn with a concentration of 1000 ppm. The color change was visually observed and the LSPR absorption was measured using a UV visible spectrometer. The detection was further at a lower concentration, 0.1 ppm, 1 ppm, 10 ppm, 100 ppm, and 500 ppm. The determination of linearity and sensitivity of the detection was measured in the range 0 until 1.2 ppm. Firstly, the detection was carried again CuZnPbCdMn with its concentration 1000 ppm. The silver nanoparticle response is observed visually through the color change of the solution among the 5 solution tests. The Cooper plus or result the most significant color change from brownish yellow to clear solution. According to UVV spectra, a significant decrease of absorbance occurred on the unlit Cooper. Even silver nanoparticle band was disappeared. The detection of Cooper was then applied on much lower concentration to determine the characteristic absorbance peak as well as the sensitivity to detection. Silver nanoparticle detected Cooper 500 ppm clearly as the color changing from brownish yellow to colorless. However, the change required a longer response time, 1.5 minutes, than Cooper 1000 ppm, which is only a few seconds. The same thing was observed when there was Cooper 100 ppm with a response time 10 minutes. Thus, a response time of silver nanoparticle to the Cooper ion is influenced by the concentration of the analyte at 1000 ppm and 500 ppm of Cooper. The absorbance of silver nanoparticle were no longer acid and the solution were colorless. In the lower concentration Cooper, the silver nanoparticle band was detected by the NCTC was reduced and shifted to higher wavelength. The sensitivity of silver nanoparticle towards Cooper was assessed by the limit of detection and limit of quantitation, which were 0.16 1 milligram per liter and 0.518 milligram per liter. Respectively, it means that the lowest concentration of Cooper that can be detected by silver nanoparticle is 0.16 milligram per liter, and the lowest concentration of Cooper that can be precisely determined is 0.518 milligram per liter. This result is quite promising compared to the colorimetric detection of Cooper using other probers. Moreover, the sensitivity can be further improved, for example, by modifying the surface of the silver nanoparticle with a capping again. LSPR absorbance measurements were also carried in the presence of other metal ions, which were Cd, Mn, Pb, and Zn. To evaluate the selectivity of silver nanoparticle probe, the result indicate that the presence of the selected metal ion did not show a significant difference to the absorbance decrease of silver nanoparticle. This means that the LSPR absorbance decrease is mainly due to the presence of Cooper, not by other metal ion. Thus, it can be concluded that silver nanoparticles are selective against Cooper.